Okay, welcome to the post-lunch session. We're very happy to have Jonathan, who's going to talk about multi-partite entanglement and replica symmetry in AdS3 CFT2.
All right, so thanks for being here on this fourth week. I know it's been for a lot of us a very long conference, and I appreciate you guys taking the time to come out today. So I'm very happy today to tell you about some work. So we have this paper that came out this January, and then Abhijit Gade, myself, and Vineeth Krishna are going to be putting out a paper hopefully sometime this month. So the focus of this work is to try and start to understand how to generalize in AdS-CFT beyond bipartite entanglement. So entanglement entropy has been a very successful tool for us using the Takayanagi formula. It has a very nice geometric interpretation in terms of the area of particular minimal surfaces in a constant time slice of AdS3. And what we'd like to do is to start to consider other measures. So is it possible to consider measures on multiple parties which have some similar geometric meaning, have some meaningful QI interpretation, and or in particular something that we're actually able to calculate. So today what I want to focus on is a particular class of measures that have gained some interest over the past year and a half. And I'm going to provide for you, in the context of AdS-CFT, in 3 bulk dimensions, explicit constructions for both the boundary and bulk of some of these measures, and I'm going to try to emphasize some general features. And a particular important property that we're going to need to discuss is something called bulk replica symmetry. So there can be cases where your boundary theory respects some symmetry and the dominant bulk solution does not. And so we will actually be able to characterize all the cases in which you can have such a measure where you're able to preserve the bulk replica symmetry. Okay, so let me first define what these quantities are. So we're calling these multi-party invariants. And kind of the idea is when we calculate a Renyi entropy, this is secretly symmetric with respect to a Zn symmetry. And what we'd like to do now is to generalize that to other finite group symmetry. So I expand it in some basis, and then taking the appropriate bra, I'm able to then define coefficients of a rank 2Q tensor, which are just the components of this density matrix when I act on it with these different states. So what we'll do is we'll choose some finite group G and consider S copies of this density matrix. And then for each of these parties, we're going to pick some group element in this group. And what these group elements do is define a particular pattern of these contractions of the density matrices. So this notation, I admit, is a bit confusing. So I think it is best to work through some examples. So first, I want to demonstrate that the Renyi entropy is in fact one of these measures. So here I'm explicitly looking at 2 parties, A and O, and we're going to look at the Renyi 4 entropy. So this will be defined on 4 copies of our density matrix. And as I said, this is secretly with respect to a Z4 symmetry, and we can choose for our single generator some explicit representation in terms of our permutations. So then to each of our parties A and O, we need to pick some group element. So for O, we just pick the identity, and for A, we will choose the element A cubed. And now we use these to perform the contractions. So for example, if I act with the identity on party O, this is the same as taking a reduced density matrix by tracing out all the degrees of freedom on O. So these right 2 indices correspond to the party A, and all I'm doing is contracting them with themselves. So taking these 4 copies of this reduced density matrix now, I now need to act on party A with the A cubed. And these instructions say that I should go from 1 to 4 to 3 to 2. So starting at the bottom index, I contract a 1 up to 4, 3 to 2, 2 to 1, and 1, or 2 back to 1. So this defines all of those contractions, and in fact explicitly computes for me this trace of 4 copies of the reduced density matrix. So this would then define this multi-party invariant with respect to those 2 group elements. So something slightly less trivial. So now let's take 3 parties, and we're now going to work with the dihedral group. So the dihedral group is now defined with 2 generators, and there's some non-commutation relation between the 2 of them. And again, we can go through exactly the same procedure. For each of the group elements, we pick or for each of the parties, we pick some group element. Those are written in terms of permutations, and using those permutations, we then complete all the contractions in order to define what the measure will be. So again, on O, we've acted with the identity. That just contracts the far right indice, and then each of these cycles represents one set of these contractions. So for example, 1, 6 here, it would be M on 1 goes up to M here on 6, and N goes back to 1. So you can verify that all of these cycles are present in this set of permutations. So this particular measure I've chosen here for D6, but it in fact generalizes to any choice of dihedral group. So the dihedral group is defined on 2 N copies, and we're going to use this class of measures as our first example to understand the calculation of these measures in AdS3 CFT2. So the goal, as I said, will be to understand this explicit calculation. And this dihedral group is in fact the simplest generalization that we can consider from the Renyi entropy, which will preserve bulk replica symmetry. Okay, so I'm going to start with talking about some of the structure of Euclidean AdS3. And in order to do that, I first need to tell you about what is happening on the boundary. So on the boundary, we are working with the Riemann sphere, and we are interested in the set of symmetries. And these are well known. They're given by the group PSL2C. And this is just the space of complex matrices with determinant 1. So these can be understood as Mobius transformations. And these can be completely classified according to the number of fixed points they have. So by simply setting this function equal to z, we can solve for what those points will be. And what you find is that there are 3 different classes depending on the sign of this depending on whether this determinant is real or imaginary. So when it is real, we have hyperbolic isometries, and you can think of these as some scaling of the space. When this is exactly 0, we have parabolic transformations, which act as translations. And when this becomes imaginary, we have elliptical transformations that act as rotations. Yes, so, okay, so good. So I'm being a bit quick here. So you can distinguish between hyperbolic transformations and loxodromatic transformations, and those will correspond to whether this is real or imaginary, yes. So you can think of loxodromatic transformations as a combination of a dilation and a rotation at the same time. This is, yes, so that is determining in the square root whether this will be real or imaginary. Yes, it's complex value, yes. No, okay, sorry. So let me say this another way. If it is pure imaginary, it will be a rotation. If it is pure real, it will be one of these dilations. But there's another case where it is mixed, both real and imaginary, and that corresponds to a combination of the both. Yeah. Okay, so these are orientation preserving isometries. And there are also orientation reversing isometries. And these will be particularly important for us. And the only difference you need to take into account is that now this should be, these Mobius transformations should be taken with respect to z-bar. So there's a particular class of these anti-conformal isometries which correspond to reflections. And for example, I can take 1 over z-bar and just again solve for the fixed points. And what I'll find is that the set of fixed points is an entire circle on the complex plane.
Is that A of z is a z bar plus b?
Yes. Sure, yes, A of z. I'm just saying it's a function of z bar. But yes, sorry. Correct, yes, exactly, yes. Sorry, that's bad notation. Yeah. Okay, so these reflections have the property that if I act with them twice, I just get back the identity. And in particular, these orientation preserving isometries can be decomposed into an even number of anti-conformal isometries. So hyperbolic 3 space, which is just Euclidean AdS3, we can view this in 2 different ways. So this is very similar in Lorentzian signature to global coordinates versus Poincare coordinates. So in the ball model, we are considering spheres which are hyperbolically spaced. Or we can also consider this on an upper half plane where t equals 0 is my boundary, and I'm now looking at this in vertical slices. So in particular, given some action of a Mobius transformation on the boundary, it turns out that there is a very natural analog in this bulk H3. So if I take this particular change of coordinates corresponding to one of these Mobius transformations, what you can find is that in this upper half plane model, the metric is invariant. So what you can conclude is that the space of isometries of the Riemann sphere is exactly the same as the space of isometries of hyperbolic 3 space. So what this is telling us is that by understanding properties on the boundary, we're actually able to make statements about what is happening in the bulk. So you can see this almost as a precursor to a holographic correspondence. And it's possible for me to relate these two pictures. So I can act now with a 3-dimensional conformal isometry. And so just like if our 2D conformal isometries, these map circles to circles, these will now map spheres to spheres. So what I can do in particular is I can map the boundary of this Riemann sphere to the plane at t equals to 0. And this gives me a way of relating these two pictures. So if I now look at one of these reflections, these anti-conformal isometries, I said that on the boundary there will be a circle of fixed points. Well, corresponding in the bulk will be a plane of fixed points, and this divides the H3 into 2 pieces. So the action of the reflection on H3 is to simply swap these 2 pieces. And similarly here, I can also have a plane this way, and this will just swap the upper and lower half. So when I translate this down to this upper half plane model, what I find is that this disk of fixed points either becomes a vertical sheet if the fixed points go through the point at infinity, or it will become a hemisphere. So just to give you some, no, good.
One slide before this.
Yes.
Okay, just one sec. So the point was that you can either work on the upper half space for hyperbolic 3 space, I guess.
Yes, exactly.
And does that cover all of?
Yes, it does. So this is a difference between Lorentzian and Euclidean signature. In Euclidean signature, this upper half space model does in fact cover up the entire coordinates. Yes. Yeah. Okay, so just to give you some idea of what these isometries look like in the bulk. So what I'm showing here is, and I've taken these from someone else. I did not make these. So what I'm showing you is on the boundary of this t equals 0 slice. And each of these dots is representing, if I was to act with this conformal isometry, where would it take me if I was to then act with it multiple times? So what this is showing is that for an elliptical transformation, I have this sense of rotation where there are 2 fixed points on the boundary. But then in addition, there is a line of fixed points extending along a geodesic in H3. So this surface here, it's sometimes referred to as a banana. This is a surface which, under this conformal isometry, would be mapped to itself. And I can imagine that these fixed points are at finite points, or I place one of them at 0 and the other one off at infinity. And similarly with hyperbolic transformations, there's a sense of movement. So again, it still has these 2 fixed points, but now the acting with the conformal isometry will move me from one of the fixed points to the other. So similarly, there is this geodesic in the bulk connecting these 2 points, but it is now not a fixed point. Instead, acting it will move me along this geodesic. Okay, so now using that framework, what I want to do for you is construct an explicit solution of a dihedral symmetry in H3 such that we can take the quotient by this set of symmetries. And when we do it, it's going to produce for us an orbifold. And what we're going to be able to use is this solution as the dual bulk solution corresponding to some boundary correlation function of twist operators. And this will calculate for us this dihedral measure. So let me explain this now. So what we're going to do is we're going to start from a spherical triangle, and we're going to choose the angles of this triangle to be pi over 2, and pi over n. And what I'll explain later is that these angles are picked to correspond to the length of twist operator insertions in the boundary. So we're going to look at this triangle in the complex plane, and associated to it, we can look at 3 circles. So these circles here extend to the point at infinity. And to each of these, we can associate a reflection, an anticonformal isometry. So starting from this triangle, we can now act with these reflections and reflect this region across each of the 3 boundaries. And when I do that, that's going to start to tessellate the Riemann surface by these 2-2-n triangles. So in particular, because these are reflections, if I just act with the same reflection again, I will return to my original region. And now we can start to label these regions by these transformations. So if I now take a pair of those conformal or anticonformal isometries, this will give me a conformal isometry. And I can now use these pairs in order to start to tessellate this Riemann sphere. And as I do this, what I will find is that there are non-trivial relations between these pairs of reflections. So for example, I can act sigma 1 to sigma 3, or I can first act with sigma 3 and then sigma 1. So that's giving me some type of commutation relation between sigma 3 and sigma 1. So continuing to do this, I can now fill out this complete tessellation. And what I find is that I need 4n of my original triangles. And this can be organized into a very particularly nice structure. So what you'll notice is that half of these are written in terms of even numbers of these reflections, and the others are written in terms of odd numbers of these reflections. And using this, I'm able to determine the explicit group symmetry that this group of these conformal isometries is isomorphic with respect to. So we can now rewrite this in terms of the conformal isometries. And then what we're able to do is to isolate a single one of the reflections. So what you'll notice now is that every single one of these regions is either written in terms of A and B, or it adds the very last operation, there will be a single sigma 1. So what we can do now is we can take a quotient. So we're just set this sigma 1 equal to the identity, and this then reduces the group down to a group of only conformal isometries. So what we've done essentially is we've taken these 2 regions, E and sigma 1, and we've combined them together into a single region. And if you now look at the group structure of these conformal isometries, it has exactly the symmetry of the dihedral group. Okay. So these groups have a very particular structure in that they are built out of these reflections. And these types of groups have been studied for a long time, and they go by the name of Coxeter groups. So in particular, a Coxeter group can be understood as being generated by some number of reflections which square to the identity. And then the only group relations we need are on pairs of these reflections up to some coefficient. So in particular, all of these Coxeter groups have already been classified, and you can associate to such a Coxeter group a graph. So the idea here is that each of these reflections corresponds to some vertice. And then if I look at an edge between 2 of the vertices, it just corresponds to whatever this coefficient here is in the group relation. So in particular, this allows us to actually classify all these groups. So this is why I'm able to look at, for example, something like this and immediately tell you what the group symmetry is, just because this has exactly the structure of a Coxeter group. And just like we were looking at with these groups of either conformal and anticonformal isometries, or just conformal isometries, Coxeter groups, you're able to take this alternating subgroup. So what this is the Coxeter group will contain half of its elements which have even numbers of reflections, and half which contain odd. And by rearranging the group elements such that you're looking at only pairs of these reflections, you're able to look at the subgroup which only contains these even numbers of elements. Okay, so what's the point? The point is that these groups of conformal and anticonformal isometries form something called a Kleinian group. And these Kleinian groups are the natural structure in order to talk about quotients of hyperbolic 3 space. So there are 2 things that we constructed. So the first is what's called the extended Kleinian group, where I'm looking at both the even and the group elements of both even and odd numbers of reflections. So this triangle here is called the extended fundamental region, and it is the region where if I act on with one of the group elements, I am not able to get back to this region unless I act with the identity. So it's saying that if I act with one of these elements, it's going to move me to one of these other triangles. Similarly, I can look at this subgroup, which is called the Kleinian group, which only contains these conformal, the orientation-preserving conformal isometries. And this is, again, looks at like a combination of both of these regions together. So if I think of this in terms of some boundary calculation of twist operators, this is like saying I'm able to map every bra into every ket and every ket into every bra. And this is like looking at a single copy of my theory, so both a bra and a ket, and the transformations only map me from one copy to the other. So it's a non-trivial fact that if I want solutions, if I want metrics which are solutions to Einstein's equations, which are hyperbolic and three-dimensional, that this is the generic way in order to produce such a solution. So I start with the full hyperbolic space, I choose one of these Kleinian groups, and I take a quotient. And so by looking at the properties of these groups, we're actually able to start to understand information about the resulting geometry. Okay.
This is an aside, but is there a reason why the Kleinian groups give all the...
Right, so you can take a quotient by this full extended group, and what you'll get is something non-orientable.
You said the Kleinian include both orientation. Oh, they only involve the orientation.
Right, so yeah, let me say that again. So there's the extended group, which includes both conformal and anti-conformal isometries. If I take a quotient by the extended group, I get something that is, does not preserve orientation. So what we're typically interested in is those which preserve orientation, and that is this subgroup which only contains conformal isometries. Yeah.
Because it's even number of reflections.
Exactly, yes, yes.
Thank you.
Yeah, so this is just to summarize. So we started with some polygon we were interested in this case, this 2-2n triangle. We defined reflections for each of those sides, and then we used these to tessellate the Riemann sphere. And from that, we were able to describe this group structure, which will describe for us a bulk solution when we then quotient hyperbolic 3 space by this group. Okay, so now I told you that to each of these reflections is some plane of fixed points. So now to every single one of these circles, I can imagine one of these planes. And what this will do is in the bulk, it will divide it into a number of cells where each of those cells is homologous to one of these boundary regions. So every statement that I made about the boundary and transformations about the boundary can actually be made as a statement about the bulk geometry. So that is a big takeaway. Yeah. Yes. Sorry, what's codimension 0? Cells. Right. No, okay, so let me say that more specifically. Okay, so here we have all of these reflections. They have fixed points. And these meet at some set of angles, right? Yeah. So what I'm saying is that to each of these boundary regions, there is some bulk cell which has these boundaries, right? So why is your boundary, why is what you are calling boundary region, codimension 0 in the boundary? These aren't intervals. No. These are copies. You can think of these as copies of my CFT. These two regions together are one copy of the CFT. The intervals that you're talking about, I haven't gotten there yet, but they live here on the boundaries. Okay. Yeah, good. Okay, so everything I said about the boundary, I can make a statement about the bulk, and now we can take the quotient by this group. And when we do that, you can imagine now collapsing this space onto a single one of those cells, and corresponding to those elliptical transformations will be this set of elliptical fixed points in the bulk. So those are exactly these intersection points between these reflecting planes. So when I do that, I'm left with a single copy of the theory where I now have conical singularities in the bulk. And the order of those conical singularities correspond to exactly the angles of intersection of these planes. So as a result of performing this quotient, we end up with an orbifold now with 3 conical singularities, where again, the group that we took this orbital fold with respect to is isomorphic to the dihedral group. So the claim is that this geometry is the correct geometry corresponding to this dihedral measure of one of these multi-party invariants. And I'll make that more specific, yes? Exactly, yes. Right, so secretly this, this line here and this line here under the quotient are the same. So I have 1, 2, and then 3. Yeah, exactly. Yeah, so this intersection point here is exactly this intersection point in the center of H3. Yeah. Okay, so this solution can actually be constructed. So what you want to do is you want to start with pure AdS3, and we're going to imagine inserting 3 conformal primaries. And the bulk dual corresponding to this is the insertion of some point mass, which back reacts to cause these conical singularities. So the way to think of this is that we have some ansatz for the metric, and we're now putting some boundary conditions at the boundary, and we want to look for a solution to Einstein's equations which solves, which has this particular set of boundary conditions. And if you go through this procedure and you find the regularized bulk action, you're able to explicitly calculate this. And what we will find is that this will exactly match with the boundary calculation I'm about to show you. So what this tells you is that this is in fact the correct bulk geometry. So in this case, we have found the solution which preserves replica symmetry, and we'll be able to show that it explicitly matches with the boundary. Okay, so let me talk about the boundary calculation. So when we are looking at one of these multi-party invariants, every time we perform one of these contractions, so I can start with some number of copies of my density matrix, and I divide my boundary into some number of regions. And every time I perform one of these contractions, because of the Euclidean path integral, that corresponds to me now starting, for example, at 1 bar, copy 1, and I'm now going to reflect across one of the regions, and I'm going to reflect to another copy. And the copy that I reflect to is given exactly by these permutations, these group elements I've picked for each party. So what this does is this gives you explicit instructions for how to build the replica manifold. So when I do this, I'm going to end up with some branched cover of the sphere. And now if I imagine I start, for example, at 1 bar, I reflect across with my group element for O. If I now reflect with A inverse, I will start to circle this point. And so what that's telling you is that I can understand this as an endpoint function of twist operators, where the correct group element to associate to those twist operators is given by this particular product of those group elements I picked for how to perform the contractions. So in order to calculate this multi-partite invariant in the boundary CFT, this reduces to me calculating an endpoint function of these twist operators where they're charged under these specific group elements. So let me make this more explicit. So first what we're going to do is we're going to take the upper half plane and we're going to conformally map it to one of these triangles with angles pi over 2, pi over 2, and pi over n. And the reason to do that is that if we look at the group elements associated with the twist operators, what we'll find is that 2 of them will have cycles of length 2, and 1 of them will have cycles of length n. So here n is equal to 3. So once we have those 2, 2n triangles, we're able to tessellate the Riemann sphere, and then we can now look at it flat on the plane. And so each of these intervals corresponds to one of these intervals here. So again, what we want to do is reflect across to some other copy where these group elements are giving us the instructions for how to assign each of the copies. So for example, this green-blue edge corresponds to party O, and I'm acting with the identity. So if I label this copy by 1 bar and I reflect across the green-blue region, then I need to label this as copy 1. And similarly, if I reflect across this blue-red edge, I'm going to go from 1 to 3, so this copy has to be labeled with 3. So using these particular group elements gives us explicit instructions on how to build up the replica manifold. And from that, just by looking at the cycles as I go around these meeting points of the triangles, it gives for me exactly the group elements corresponding to the twist operators. So 1 goes to 2 goes to 3 is just this cycle here. Okay, so now in order to calculate what this endpoint function is, the correct way to do this is we've now constructed the Riemann sphere, which is tessellated, and what we want to do now is conformally map back from the Riemann sphere to the branched cover. So there's a particular map that allows you to do this, and it goes by the name of a covering map, and it has some specific properties. So I'm not going to have time to go through the full calculation today, so I just want to give you a flavor for what this calculation looks like. And in particular, as a result of this, given my twist operators, I'm actually able to extract a lot of information out. So you can show that my twist operators have some specific conformal dimension, which is a function of the lengths of the cycles and the number of cycles. And when I perform this tessellation, based on the twist operators I've inserted, I will actually know what the genus of the replica surface has to be. So in this case, we were looking at something with genus 0. So once we've determined what this conformal map is from the Riemann sphere back to the branch cover, we're able to use the Liouville action to explicitly determine what the change in the partition function will be. So here, we've written some change of coordinates in terms of this Liouville field. And by determining all of the contributions to the Liouville action allows us to determine this conformal anomaly, where here this is the partition function of the Riemann surface, which is the replica surface, and then a number of copies of the sphere partition function, which is equal to the order of my group. So in particular, once I know this higher genus partition function and this covering map, I'm able to explicitly extract out what the endpoint function of the twist operators are. So the caution here is that this Liouville action is divergent, and you have to work really, really hard in order to regularize it and get out some answer. And doing that calculation would be a talk in of itself. So today I'm gonna take this as this is something you're able to do. And if you want to ask me more questions about it later, I'm very happy to talk about it. Yeah?
Not to the calculation, but why is it divergent in compact space?
Okay, so you need to, this covering map is divergent, right? And it will diverge exactly at the, so all of these points here correspond to pre-images of the twist operator insertions under the covering map. And these are the points exactly where it will diverge. So this has to do with the structure of the covering map. This is something you can prove. That it's phi going, yeah, yes, phi is going to infinity, yep. Yeah, okay, great. Exactly, yes. So you need to basically cut out some disk and use this to regularize it. You need to keep track of all of these cutoffs, and at the end, you need to make sure all the cutoffs go away. Yeah. Okay, so now the point here is that these constructions are extremely similar to one another. So in the bulk, we were able to construct this particular set of symmetries where once we've constructed it, each of these meeting points of my fundamental region, these correspond to some elliptical fixed point of a conformal isometry in the Kleinian group. And when I build up my, my replica surface, I'm essentially building up exactly the same tessellation, where now the vertices are corresponding to the pre-images of my twist operators under this covering map. So in fact, it is possible to extract the information about this covering map from the Kleinian group. So that's what I want to go through next. Okay. So these covering maps have a very particular property that they are automorphic. And what this means is that if I act with some element in this Kleinian group, it has to be invariant under that transformation. So what this actually implies is that in this fundamental region, these two triangles together, this function has to take the values 0, or has to take all the values of the complex plane exactly once. And it will have critical points, again, exactly at these elliptical fixed points, which correspond to the meeting points of the triangles. So you can show that given these properties, if my replica manifold is genus 0, then this function has to be rational. So this actually gives us an explicit way of constructing what this map is. So what I'm going to do is I'm going to take all of these elliptical fixed points, and I'm going to separate them into 3 groups. So all the blue points, all the red points, and all the green points. And I'm simply going to list all their locations on the complex plane. And now we're going to construct a polynomial whose zeros are exactly these points. And we're going to multiply it by the cycle length of the corresponding twist operator. And when we do that, we can construct the ratios of these polynomials. So the roots here of P1 are the points being mapped to 0. And the roots of P3 are being mapped to infinity. But we also want to fix one more location, and that will be that we want these roots of P2 to be mapped to 1. So what I can do is I can look at the 1 minus f of z. So this is just a conformal transformation of f of z. And so now under this, if I set this equal to P2 over P3, I'm now saying that all of these roots here should be mapped to the point 0. So what this implies is that these two polynomials have to be related to one another, and it gives me a linear relation between the 3 of them. And solving this then gives me exactly this covering map. So again, this map will have critical points exactly at these points here. Okay, A and B are independent of Z. Yes, they are just constants. So this is a very non-trivial fact that there exists some relation like this between the polynomials. And there's some, I don't fully understand this. I would just say that there's some connection to Galois theory. So you can prove that such a relation has to exist, yes. Okay, so using that covering map, we can go and explicitly calculate what this endpoint function is. And again, you can then show that this matches exactly with the bulk solution that I constructed for you. Okay, so I'm running low on time, so I'm gonna speed up a little bit. Okay, so what I constructed for you was some genus 0, a measure which had a replica surface which was genus 0. And it turns out that there are only a finite number of ways you can do this. So these correspond to this dihedral symmetry, and then there are also symmetries corresponding to platonic solids. So all of these are finite subgroups of SO3, and in all of these cases, we can go through the exact same procedure. You can explicitly construct this Kleinian group, get the quotient, and get some orbifold. You can explicitly calculate these as 3-point functions of twist operators, and you can show explicit matching. So this, in fact, this is all of the genus 0 measures you can show which will preserve bulk replica symmetry. And I will be able to explain that in a little more detail. Okay, yes, so that's this statement here. So all of these spherical groups, which are finite subgroups of SO3, I can go through the same procedure, and I'll end up with an orbifold with some particular pattern of conical singularities. And these are the only ones. Okay, so we're going to start to transition to higher genus. And what we're going to be interested in is now our replica surface is not going to be genus 0. It's going to be something of higher genus. And what is known is that when I'm doing some saddle point approximation, that the dominant contributions will be handle bodies. So these handle bodies you can think of as a Riemann surface which has been filled in with hyperbolic space. So it's sometimes denoted as some genus G Riemann surface times an interval. And you can show that these handle bodies are examples of quotients of H3 by very special groups, which are called Schottky groups. So these are freely generated, so there are no relationships between the generators, and they're hyperbolic, so they only consist of hyperbolic isometries. And what you can show is that the allowed symmetries of these handle body solutions is in fact much less than the allowed symmetries of Riemann surfaces. So in particular, if I construct one of these replica surfaces and it has this higher degree of symmetry, I can be in a situation where it is not possible for me to find a handle body solution which has that same set of symmetries. So what this is saying is instead of trying to preserve all those symmetries, I should instead fill it in with a handle body and break some of the symmetry. So this is the statement of it not being bulk replica symmetry preserving. Okay. Yeah. Yeah.
First question is you constructed a solution to the
Yes.
Does that mean?
Well, no. So this is the point. At genus 0, there are very specific Kleinian groups which allow you to construct these quotients. and there are no others. Like, there is no other solution I can construct with that symmetry. Yeah, yeah. This has to do with the fact that it's a 3-point function. Like, there's no moduli to tune. Yeah. So this is at the moment specifically for vacuum ADS. So I don't have anything other to say. Yeah. Yes.
At genus 0, so if I understood, given the data of what the twist angles, etc.
Yes.
On the boundary, there's a unique geometry in the bulk.
Correct.
Which sort of fills that.
Yes.
Right?
Yes.
Which preserves the replica.
Correct. Yes.
But could there be a filling in which breaks the replica symmetry in the bulk?
Sure, but I believe in those cases you can show that it will have higher action. Like, we haven't explicitly done that, but yeah, I believe that would be true.
That sounds very reasonable.
Yeah. Yes. No. Yeah. I think the fact that we can get this explicit matching on the bulk and boundary is kind of the nail in the coffin for that. Yeah.
So you get to imagine the final answer for the bipartite.
So for this class of for all these measures that correspond to those which have genus 0 replica surfaces, you can show that this bulk solution with the 3 conical singularities, I compute its gravitational action, that will, up to some normalization, exactly match this 3-point function of the twist operators.
Okay,
Yeah.
so you exactly match.
Exactly. Yes.
Then
Yeah.
of course it's there.
Yeah. Okay. Okay, yes, so these Schottky groups, this is more or less what I just said. I just want to emphasize that you can understand these in the Riemann sphere as I'm going to have, for each genus, there's going to be some circle. And what these Schottky groups do is they take you from one circle to another circle. So in the bulk, this corresponds to I have some hemisphere, and I'm going to identify those hemispheres together. And when I do that, I end up with some genus G surface. And this is the only way you can construct such a handle body solution. So I'm going to need a minute to explain this. So what I want to give you is an example of when this fails. So in the following sense. So let's imagine that I want to insert 3 twist operators whose cycles are of length 2, 3, and 8. And I'm going to go through the exact same procedure. So I'm going to find some triangle with angles 2, 3, and 8, and I'm going to start this process of reflecting. And when I do this, what I find is that there are now an infinite number of these triangles that are needed in order to tessellate the Riemann surface. So I've hidden the remaining infinite number of copies behind these circles. And so, in fact, what you can show is that there will be an infinite number of hyperbolic isometries, each of which has 2 fixed points. And that set of fixed points lies exactly along the unit circle. And what this does is it splits the sphere into 2 disks. So what I can do is I can look now for a subgroup of this group such that if I quotient by it, I end up with a finite group. And such a group exists, and this is an example of something called a surface group. So you'll remember that when I was looking for a Schottky group, I was trying to identify circles with one another, and that is exactly what I'm doing here. I'm identifying these circles, but because the circles overlap with one another, there's in fact a non-trivial relation between these conformal isometries. And this relation is exactly the group that is needed to quotient the hyperbolic disk by to get a Riemann surface. So here you can view this as one copy of part of the hyperbolic disk tessellated by these 2, 3, 8 triangles. And outside the circles, I have exactly the same pattern of these triangles. So when I take this quotient by this surface subgroup, what this does is on the boundary, it splits the geometry into 2. So each of these will end up being a genus 2 surface. And in fact, for any experts, this is the Bolas surface. So it's the most symmetric genus 2 surface you could possibly have. So we immediately know that its group of automorphisms is higher than that of a handle body group. And in the bulk, these 2 boundary Riemann surfaces are actually connected to one another. So this is an example of a Euclidean wormhole, one of these Maldasenas-Moaz wormholes. So the fact that this line of hyperbolic fixed points is the entire unit circle, that is actually immediately enough to tell you that this group contains no Schottky group as a subgroup. So back to this calculation of this 3-point function, if I wanted to try and find a geometry that would correspond to a quotient which had this full set of symmetries, it would be impossible for me to find a geometry which had this full set of automorphisms, unless I include some extra boundary. So the statement is that it's better to break some of those symmetries and fill this in with a handle body, and that should then have a lower gravitational action. So this would be an example of a measure which we can tell it will explicitly break the replica symmetry. And the key identifying piece here is whether we are able to find a Schottky group. Okay, so I'm pretty low on time, so I am going to skip some things and just kind of get to the... Yeah. I'm about like 2/3 of the way through. Yeah. Okay. So, anyways, so this is the punchline. So, what we want is we want a Kleinian group, and we want it to have a Schottky group as a normal subgroup. Because if it has one of these groups as a normal subgroup, we can take the quotient by the Schottky group, and we'll end up with it as a handle body with some set of symmetries. You can prove that if you want a group with this property, it either has to be a finite group, or it has to be built from finite groups in something called a free amalgamation. And I'll define this as in a second. So what we were going to use is these spherical orbifolds. We're going to use these as building pieces to construct some more complicated solution. So the idea will be that, for example, we're going to take two of these dihedral groups. This will correspond to, on the boundary calculation, 4 twist operators, and we will join them across this common end. And when I take the quotient by this new group, what I'll end up with is exactly an orbifold with this set of singular loci. Okay, so yes, so that's exactly what we're going to do. We're going to take these two dihedral groups, and we're going to combine them across this common end. In this operation of free amalgamation, I just take these two copies of the group, and I squash them together, except because the amalgamation is over this group J, we're now going to identify C and D together. And when I do that, I end up now with an infinite group. So it turns out that there is a geometric way of understanding this operation of free amalgamation. And we can use this now to construct for us the bulk geometry. So what I'm going to do is I'm going to take 2 copies of this dihedral group. So I have 1 copy here. And you remember that this is the extended fundamental region associated with this dihedral group. And now I'm going to do take a second copy, and I'm going to transform it in some way. So what I'm going to do is I'm going to start with the second copy, and I'm first going to act with a reflection. So instead of thinking of this fundamental region, I can instead think about this fundamental region. And then I'm just going to act with a scaling transformation. So I'm going to take this circle from 1 to radius 1/p. And you can show that this leaves the symmetry of this Kleinian group, it leaves it the same. So these two groups are conjugate to one another. So now with these 2 fundamental regions, what I'm going to do is overlap them in such a way that they are symmetric with respect to this common Zn symmetry. And now I'm going to use this new polygon with 4 sides and angles of pi/2 in order to construct a new group. So I'm going to go through the exact same procedure. I start with this fundamental region, and I just start reflecting it. And what I find now is that there are an infinite number of these polygons that are needed to tessellate the Riemann sphere. And what this is indicating for you is that this group now contains hyperbolic isometries. So when I look at this, I can identify that this element AB is acting as a dilation. And what it's doing is moving me out in this radial direction. So in fact, this is the generator of a Schottky group, which now lives inside of this larger Kleinian group. So this is called a virtual Schottky group. And if I take the quotient of hyperbolic 3 space by this Schottky group, I'm identifying these 2 hemispheres. So there's a hemisphere here and a hemisphere out here, and they're identified together. And what I will get now is a solid torus, a handle body geometry. So if I take the quotient of my original Kleinian group by this Schottky group, I will end up with a finite group, which is exactly the automorphisms now of both the boundary Riemann surface and the bulk handle body. So I'm gonna skip some, okay. So I'm gonna go to here real quick. So I have a choice of how to take the Schottky group. So I could have taken the Schottky group, the entire Schottky group, or I could have taken some subgroup of it. And what that corresponds to is keeping more copies in this radial direction. So as I am quotienting by this coarser Schottky group, I'm now getting a new set of automorphisms for what corresponds to a different handle body and boundary Riemann surface. And these will correspond to different measures which are built out of different numbers of copies. So I have two choices here. When I did this amalgamation, there was a choice of what value to take for n, and there's also a choice of how many copies I can keep in this radial direction. So what you can do now is you can consider two different amalgamations. So for example, I can take these to be dihedral groups of order 4. So this is like putting 2 copies in this angular direction. And I can take the number of copies in the radial direction, so this choice of Schottky subgroup, to be 3. Or I can instead take my groups to be D6. And now I'm putting 3 copies in this angular direction and 2 copies in the radial direction. So in fact, these two solutions have the same set of boundary automorphisms. So what we've actually done is we have constructed a handle body, and using a different group, we've constructed an S transformation of the handle body. So I've taken the contractible and the non-contractible cycle, and I've switched them. So what this is indicating is that there are 2 different phases, and the phase will correspond to which of these values, n or m, ends up in the singular locus of my handle body. And you can go through the exact 4-point function calculation on the boundary, including the torus partition function, and you can find the phase transition between these 2 solutions. So what I'm plotting here is the cross ratio of the twist operators, along with the partition function for the m lotus here in blue and the n locus here in orange. So if n and m are taken to be the same, then the phase transition happens at exactly the 1/2 point for the cross ratio. And this is maybe the normal solution you're used to seeing for the Renyi 2 entropy on 2 intervals. Now, if I take n and m to be different, then what happens is that this phase transition gets moved such that for almost the entire range of the cross ratio, I'm in the phase where this central singular locus has the smallest order. So in fact, you can prove now that this is the only possible way of getting a replica preserving 4-point function of twist operators, which is genus 1. So this completely exhausts now genus 0 and genus 1. So okay, so I'm ready to conclude, and I have some more things I can say at the end if people are interested. So I've shown for you that this new class of measures, which we call multi-party invariants, and these have the property that they can be constructed from density matrices and then contractions of these density matrices with respect to some group. And as a result, unlike many measures you might think of in quantum information theory, these are relatively easy to calculate, and hopefully they have broad applications to other systems. So it'd be very easy now to take some class of these measures, go to some system that you're interested in, and explicitly perform calculations and try to understand more about what these quantities mean. I showed you that we can understand in AdS3 CFT2 how these can be geometrically constructed, either from Kleinian groups or from endpoint functions of twist operators, and how they can be calculated and how those calculations are related to one another. So we're still working on general quantum information properties, how these measures can be understood and related to one another. And we're also working on now higher genus. So as I said, we've completely exhausted genus 2 and genus 1. And then I showed you this example of this multi-boundary, or this Euclidean wormhole. So these Kleinian groups are generically able to construct many solutions which are not handle bodies. And it'd be very interesting to also try and understand what their applications are in AdS-CFT. Right, so I'll end there, and I'll just say that I have some things I can say about genus 2 if people are interested. And yeah, I'm happy to take questions now. Thanks.
Yeah, I think we're doing good with time. We have time for a few questions.
No, I'm not sure. Thanks a lot for a great talk. I'm not sure I understood the motivation for going to, say, genus 1, which is to say, was it that for some multi-partite measures on the boundary, if you were trying to compute them on the boundary, you were forced to go to higher genus surfaces in the bulk? Or
Okay, so here's the statement. I'm going to insert some number of twist operators on the boundary.
Correct.
Based on those twist operators I inserted, I can prove for you what the genus of the replica surface will be. So this is this Riemann-Hurwitz relationship. And so the point is that I showed you that in order to have something that preserves the bulk replica symmetry, if it's a 3-point function, it has to be one of these spherical groups, or I have to build up the group from these spherical groups. So if I was looking at 3-point functions, I already computed for you all of the possible 3-point functions which can have preserved bulk replica symmetry. So at that point, the next thing to do is to go up to a 4-point function and look at something that's genus 1.
Thank you.
Yeah. Yeah.
How do you prove that there are no other? In the genus 0 case, how do you prove that there are no other geometries?
Right. Okay. So first of all, you can prove. So this is again using this Riemann-Hurwitz relationship. Oh, yeah. So this guy here. So once I know my twist operators and the lengths of those cycles, I can use that to tell you exactly what the genus of the replica surface has to be. So you can prove that if I have 4 twist operator insertions, immediately it has to be genus 1. So if I want something that's genus 0, it has to be a 3-point function or less. So in terms of these Kleinian groups, what that's telling me is that I can only have 3 generators, which are elliptical elements. And using that, you can then prove that there are no other possible finite Kleinian groups other than the ones that I showed you. And it essentially boils down to exactly this relationship. So you look at you look at this relationship, you ask what insertions of twist operators can I perform such that it'll stay genus 0, and this classification exactly pops out. These are the only possible ways of getting such a group.
And why is it clear that every solution has to have something to do with the Kleinian group?
Sorry, it has to have such a what?
Why does every solution have to have something to do with the Kleinian group?
So I don't know the full statement, but there is a statement you can make, which is if you want solutions to Einstein's equations with a hyperbolic metric, all such solutions can be found as quotients of H3 by some Kleinian group. Yeah. So this is some statement about the fact that you're in 3D and things are very constrained.
A bit of a naive question, but from the boundary, the measures that you define seem to be very general, but from the bulk perspective, they seem to be engineered for AdS3 CFT2. Is there a hope of doing these in like higher dimensions? Or?
Right. So the Coxeter group. So what I showed you are Coxeter groups with 3 generators. So if I go to 4 generators, you can actually think of these in terms of tetrahedron. And so you could imagine something like a quotient of H4, now where your boundary is S3, and you're taking the quotient by some higher generator Coxeter group. These are words you can put. Like this is definitely something that is possible, and I know it's something Abhijit's like very interested in, but at least for this project, it's not something we pursued further than that.
Okay. But can you calculate the actions and stuff?
Oh, yeah, I have no idea. Possibly.
Any more questions for Jonathan? Okay, if not, let's thank him.